Goedemiddag allemaal en welkom bij de lunchlezing over lassen, het nabehandeling van lassen met behulp van High Frequency Mechanical Impact. Professor Mohammad Al-Emrani van de Technische Universiteit Chalmers in Göteborg zal ons het komende uur vertellen over het onderzoek dat hij de afgelopen 15 jaar heeft gedaan na deze behandeling. De lezing zal overigens in het Engels worden gegeven. Vragen kunnen jullie allemaal stellen in de chat. Ik zal ze achteraf aan professor Al-Emrani stellen. En ik wil verder iedereen vragen of jullie je microfoon kunnen muten. So, Professor Al-Emrani, can I now give the floor to you?
So I hope my screen is visible for everyone.
Yeah, your screen is visible. Thanks. Yeah.
Great. Yeah, thank you very much for inviting me to this talk, which I will devote to high frequency mechanical impact treatment, particularly application on bridges. The bridge that you see on, by the way, on the first slide is a bridge in Gothenburg, the city where I am located. And it's a bridge that was built in 1964. It's going to strengthen now by welding new details to the bridge to hold the suspension cable. And these details will be HFMI treated also to obtain a better fatigue performance. So I was told that I should expect a wider audience for the talk. Therefore, I would like to start with a couple of slides, maybe not to take the topic of fatigue. I assume that almost everyone here knows fatigue and fatigue problems in bridges. But I would like to start by taking a couple of slides to take some characteristics of the fatigue behavior and the fatigue performance of welded connections that we would need with us for getting into the HFMI treatment. And then I will mention a little bit about post-weld treatment in general, different methods that can be used to get into the main topic of high-frequency mechanical impact treatment then. And there I will start by defining what is HFMI, what we mean by it, and how it works in terms of fatigue, improvement of fatigue strength, and particularly put some effort on getting into the implications of using HFMI on the design and verification, fatigue verification of welded details. And later also take a look at the possibility of using this technique, high frequency mechanical impact, also for the purpose of fatigue life extension of existing bridges, not only for the design of new bridges. And then I will conclude with some information about technical requirements on welds before applying the technique or the method, after applying HFMI treatment, and which quality assurance or quality checks should be done on welded details that are HFMI treated. And if we have time, I will show a couple of examples on bridges in Sweden where this method has been applied, both on the new bridges and on existing bridges. So that's a little bit the agenda for my talk. And starting just in a general sense, looking at welding and how welding influence the fatigue performance of welded details, which we find in all modern bridges today, and in particular, two aspects that are very important to consider and that have serious implications on the performance of welded details with reference to fatigue. The first one is the presence of weld imperfections or weld defects of different types, undercuts, porosity, lock effusion, and so on. And these will be in principle very serious local stress raisers. They will perform or behave like small micro cracks. That makes the fatigue life of welded details in principle mainly crack propagation, as we have defects that more or less are small micro cracks. The second aspect is, of course, the presence of residual stresses. We assume, and we often get high tensile residual stresses in welded details in areas which are critical. and that also has its influence and its implication on the fatigue performance of these details. So what these two factors do in principle is that, to start with, they reduce the fatigue strength of welded or of the steel as of the base metal substantially. So we get lower fatigue resistance by introducing these welds. And that's partly in principle due to the fact that we don't have crack initiation or very limited crack initiation phase. The second implication of that is that we also lose the dependency that we otherwise have in the base metal of the fatigue strength on the tensile strength. So if we are just looking at base metal performance without influence of welding, we see that we have higher fatigue strength for higher strength steel. This dependency becomes much weaker and more or less disappears when we introduce welds and weld defects in welded connections. And that is, of course, the reason that when we do design, fatigue design today, for as welded details, we don't consider the strength of the material as a parameter. So whether we have high strength steel or conventional construction steel, we don't care in the fatigue design. We don't take this into account because of this reason. And this makes, in principle, in practice, the use of high strength steel in fatigue loaded structures, or at least in these structures in which fatigue is designing or determining the design, not relevant because of that reason. So these two implications are, of course, serious in terms of fatigue performance due to introduction of welding and the welded details. Now, when we are looking at the fatigue strength, we usually describe this with SN curves. These are commonly parallel slope SN curves. The curves that you see now are those in the presence version of Eurocode. And we have curves from the highest, which is 160 megapascal at 2 million cycles, that describes the base metal, into the lowest SN curve, which is 36 then. And these curves cover all kinds of welded details that we can find in bridges, or at least they are meant to do that. But we can categorize, one way of categorizing these welded details is to look at details with very low fatigue strength, the lowest curves, and these refer to mode of cracking, which we call root cracks. These are cracks that initiate and grow through the weld itself. And these kinds of fatigue cracks have very low fatigue strength, but they can mitigate it or they can be avoided by increasing the weld throat thickness, having bigger welds, or prescribing partial penetration or full penetration welds in design, so to say. The second category that we can identify belongs to these details that have very high fatigue strength. And in this category, usually fatigue crack starts from inner weld defects or inner weld imperfections, such as porosity, lack of fusion, and so on. And typically, these are not determining the design of steel bridges, for example. They have such high fatigue strength that they are not setting the roof in the fatigue design. Between these two categories, we have the category which is often determining the fatigue design of welded details, for example, in bridges. These are welded details that have intermediate fatigue strength, something between 50 and 90 detail categories. And in this category of details, fatigue cracks starts typically from the weld toe region. And we see these details in many types of bridges, orthotropic bridge decks, bridge girders with different types of details. And in all these details, then cracking starts from the weld end or from the weld toe and grow in the base metal. So they are typically determining the fatigue design. They put the limit for which stresses we can allow for a specific design lifespan then. Now, if we would like to enhance or improve the fatigue performance of welded details, particularly the type or the category that we are looking at here, in which fatigue crack starts from the weld toe, there are in principle three methods that we could do, or three actions that we can take. The first one refers to reducing the stress concentration at the location of crack initiation at the weld toe by having a smoother transition between the weld and the base metal. The second option, or the second action that one could take, is by removing possible undercut or other surface defects that exist in this location. And the third action refers to the presence of residual stresses, which often are tensile residual stresses, high tensile residual stresses, that we can either relax or, if possible, introduce in terms of compressive residual stresses. And that would enable us to improve the fatigue strength then of the detail with reference to cracking at this location. So these are, in principle, three different actions that one can think of with the objective to improve the fatigue strength of this kind of details. One method that has traditionally been used before is to use burr grinding with at the weld toe. By grinding the weld toe, we have a better transition from the weld to the base metal. We get a lower stress concentration, and if there are any surface defects, micro cracks or undercuts at this location, then we remove these as well. And that would result in enhancement of the fatigue strength, typically 1 to 2 detail categories better than the as welded condition. So this is a method that has previously been used before. Second method that should be mentioned here is to use TIG remelting or TIG dressing. The principle here is to remelt the region at the weld toe in order to arrive at a smoother transition of the area where at the weld toe where typically we would get toe cracking. And by doing so, we also get a better fatigue performance. Also typically 1 to 2 detail categories better than the as welded condition. So these are two, let's say, traditional methods that have been applied or used before. Another method that has gained a lot of interest, maybe the last 20, 25 years, is what is called then high frequency mechanical impact treatment. And that's what my talk would be around today. So the term high frequency mechanical impact treatment covers or include different technologies that have been available that have in principle the same working mechanism. The local area at the weld toe, which is the critical region where cracks initiate, is then hit with a hardened pin with very high frequency, resulting in plastic deformation of this area, cold working of this area, which has several beneficial effects on the fatigue performance then of the weld toe. So it's a very local treatment method that is particularly working with respect to fatigue cracking at the weld toe. It doesn't have any influence on details where we expect to have crack initiating from the weld root, or in details in which the crack would initiate from inner weld defects like porosity and so on. But they are particularly for these weld category, or this weld category, the intermediate one that I showed before. So to show how this method in principle works, I have a short video here that it was taken from a bridge in Gothenburg where the HFMI was applied on approximately 480 details of orthotropic bridge deck. I hope that the voice or the sound is not very high. That's in principle how this HFMI tool is working. Very high frequency hit of this hardened pin on the weld toe region, causing very localized plastic deformation there. What we see here is a treatment of the weld between a longitudinal rib and a cross beam in an orthotropic bridge. So this cold working that is taking place very locally at the weld toe region has three principal influences that are important for the fatigue performance. The first one is that it deforms the material at this location and improves the situation in that term, that it reduces the stress concentration, it gives a smoother transition from the weld metal to the base metal in this region. The second and much more interesting and important effect is that this cold working of the material and the plastic deformation result in local high compressive residual stress, which is very important for the fatigue performance. So from the as welded situation, in which we usually have tensile residual stress, we have now a situation in which we have compressive residual stresses, which are beneficial. And the third effect that is obtained from this treatment is that due to the cold working and the plastic deformation, we have increased hardness and increased local yield strength of the material in the region, which is critical from the point of view of fatigue. The compressive residual stresses will depend on several parameters, on the intensity of treatment that you can set in the tool which is used, on the type of steel or the strength of steel that it is treated, and so on. But it's typically something between 1 and 2 millimeter deep below the surface, and it can go up to very high stresses in compression. And they stand for the major part of the enhancement that this technique is performing. So it's very important with these compressive residual stresses in this kind of treatment that we actually, of course, don't have neither with the bore grinding nor with the teak dressing in principle. This transition of the weld toe region and the radius that we get there will also depend on the pin radius used or the pin diameter. You see here the measured R or toe radius from as welded and HFMI treated details when the HFMI treatment was done with a pin with a diameter of 3 millimeters. So the radius, the mean value of the radius is lying around 1.5 millimeter then. And of course, the increase in hardness and the increase in local yield strength of the material would result in turn into a higher resistance to crack initiation in this location, which also has an influence on the enhancement in fatigue performance. So all these three effects that are obtained from the HFMI treatment will result then in restoring of the fatigue properties from that we got the lowered fatigue strength that we got due to welding into something that is close to the performance of the base metal. So we have a higher fatigue strength, and more importantly, actually, we have even a shallower slope of the SN curve, because we are again reintroducing the crack initiation phase into the fatigue resistance of the welded detail. Another implication, which is very important and a particularity for HFMI treated details that needs to be accounted for in design, is that we restore also the dependency of the fatigue strength on the material strength. So now having higher strength steel enable us or entails us for also having a higher fatigue strength. And that is very important application, at least for application in new bridges, that would enable us in design of new bridges also to utilize the benefits of higher strength steel in many applications, which was, of course, not possible when just using as welded details. Another implication which is important and a particularity that we need to take into account in terms of design is now that the fact that the fatigue strength now becomes dependent also on the R ratio. So while this aspect is not accounted for or considered when we design currently welded structures in as welded condition, with HFMI treated details, load cycles with the same stress range, but with higher mean stress or with higher R ratio, will be more damaging than the same load cycles with the same stress range, but with lower R ratio or with lower mean stress. And this influence of the R ratio needs also to be accounted for, of course, in the design. So this is the second implication. In addition to FY, the R ratio needs to be accounted for. The third implication of using HFMI that also need to be considered in design comes from the fact, which I mentioned before, that the major part of contribution HFMI does in increasing the fatigue strength is coming from these compressive residual stresses. So at least theoretically, any overload or any situation that would result in local plasticity at the well-toe that will shake down or relax the compressive residual stress would have a negative influence on the degree of enhancement or the degree of improvement that can be achieved by this method. So there should be a limitation for permissible or allowable stresses on HFMI treated details so that we don't exceed these limits and result in a relaxation or a reduction of these residual stresses. So these three aspects, the FY influence, the mean stress influence, and the possibility or the limitations for maximum load need to be considered in terms of design. And that is in principle what at least partly is covered by the recommendation that is given in the upcoming version of your code, part 1.9, in Annex F, which covers the use of HFMI. There are, of course, other recommendations. I mentioned here the one given by the IIW, the International Institute of Welding. But in my talk today, I will focus on what is in Annex F, of course, because it's more relevant for us in the bridge industry in application. So to start with, we look simply at the SN curve. The dotted line here shows the SN curve for the as-welded detail. As familiar for everyone, we have bilinear SN curve with two slopes, 1 to 3 and 1 to 5. And what we achieve by doing HFMI treatment is partly increasing the detail category or the fatigue strength from delta sigma C to delta sigma C HFMI, which is higher. And the second thing we are doing, of course, is that we are changing the slope of the SN curve. So instead of 1 to 3 and 1 to 5, we have a slope of 1 to 5 to 1 to 9. And that adds, at least in the large number of cycle regime, an additional value from this HFMI treatment. There is a new point or a knee point introduced, which is called delta sigma S. At least theoretically, this is the point of intersection of the new SN curve for HFMI with the corresponding SN curve for as-welded details. And what this knee point is telling is that if we have stress ranges that are higher than delta sigma S, or in other words, we have a number of cycles that are less than N minimum HFMI, then we don't get any benefit of HFMI treatment. This is hardly the case in bridges, but in principle, this is the situation or a check that needs to be done, that we don't exceed this limit of delta sigma S then. In the current version or the upcoming version of Eurocode in Annex F, there are in principle these three details that are covered: transverse butt welds, transversal attachment, non-load carrying attachments similar to vertical stiffeners and plate girders, and longitudinal attachments. And for each of these three details, a detail category, the reference delta sigma C HFMI is given. So either 160, 140, or 100, and you see directly that we are leveling up the fatigue strength. For example, for transverse attachment, it's 71 or 80, depending on the thickness of the attachment. And we are leveling this up to 140, which is very close to the base metal fatigue strength. But this is the reference value for the fatigue strength. Now, this reference value doesn't take into account the yield strength of the steel, and it doesn't take into account the R ratio effect. And in order to do that, then this reference value is corrected with two factors, F1 and F2. F1 is a factor that takes into account the yield strength of the steel. So you see with increasing yield strength, then F1 increases, and thus delta sigma C HFMI would be larger or will increase as well for higher strength steel. Second is the correction factor for R ratio, and this is given by this expression, which then it says for R ratios less than 0.1, no correction is needed. If R ratio is higher than 0.1, then the correction will follow this curve. And what we are doing is then we are reducing the benefit of HFMI treated for load cycles with higher R ratio. So for each detail, there is delta sigma C, HFMI reference, and then depending on the yield strength of the steel material that is used and the R ratio, then this is corrected into a design fatigue resistance to be used. Also based on large number of experimental work and a lot of numerical analysis done, limits have been identified for these three different types of details in order to avoid the situation I mentioned before of having overloads that would result in relaxation of the compressive beneficial residual stresses. And because these residual stresses are in compression, the limits on the tension side are generous, so they are Fy. We shouldn't allow stress in tension that is bigger than Fy. That shouldn't be a problem. On the compression side, the limits are different for different details because different details have different stress concentration in principle. So for butt welds, we have 0.9, for transverse attachment, minus 0.7, and for longitudinal attachment, minus 0.5. So load effects in the structure that we are treating with HFMI should be within these limits in order to ensure that we don't get any relaxation of the residual stresses. That is what is stipulated in then the upcoming Eurocode, Part 19. So on the resistance side, we have rather good control of what we should allow and how we should treat both the R ratio effect and the Fy effect, and also in terms of the limits for allowable stresses. Questions arise how designers should apply these rules, because real traffic loads on bridges are much more variable than what our load models in Eurocode represent. And we could have load effects that are, of course, much larger than what the load model, fatigue load model produce, but also we have a lot of variation of loads that would result in a variation of the R ratio. So we need somehow a model to account for this variation of the R ratio effect from real traffic. And we also need to answer a question, which loads or load combinations we need to include in order to check these limits for permissible stresses or allowable stresses. And I will not go into details of the background of this, but just to mention that a lot of work has done on these two questions. And this is mainly based on extensive measurements, traffic measurements on road traffics and railway traffics. The road traffics is coming both from Sweden and from the Netherlands. And these vehicles or lorries that are measured with their axle loads and axle distances were used in simulations on different bridges with different influence lines and simply supported continuous. And then this was used together with fatigue load models, both fatigue load models 3 and 4, in order to correlate real load effects into the load effects that are coming from the load models that are used by designers. And the result of this is some kind of derivation of some kind of correction factor. And this correction factor, which is called here lambda HFMI, is then used to reflect or describe the variation of R ratio from real traffic on bridges in correlation to the traffic load model that is used by the designer. So it's similar to lambda 1, for example, that is used in the simplified fatigue design in the Eurocode. So the fatigue verification format is very similar to the one that we have for as well the detail. Delta sigma E2, now HFMI, of course, is the equivalent stress range at 2 million cycles. This is related to the fatigue resistance, HFMI, modified with the factor F1, which takes into account the Fy effect. And the R ratio effect now is put on delta sigma E2, similar to lambda 1, lambda 2, lambda 3, with a new lambda factor, which is lambda HFMI. And this lambda HFMI was derived from these traffic measurements that I mentioned before. So in a very similar way to lambda 1, in the current rules for fatigue design, we distinguish between the support section and the mid-span section. We have two curves that describe lambda HFMI, dependent on phi, which is a factor that describes the stress range, delta sigma p, and the mean or the minimum stress that is coming from all permanent loads. So phi sigma permanent divided by twice delta sigma p. That describes the R ratio effect coming from the load model, and then it's correlated to a lambda HFMI, which is then used on the load effect side. So for road bridges, this was derived, and similar curves are derived for railway bridges. Of course, if we have a situation in which HFMI is performed when the bridge is erected and the permanent loads stresses are in place, then phi equal to 0 can be used, and the value of lambda HFMI would be very small. Otherwise, we will end up with a higher lambda HFMI, which will reduce, let's say, the benefit of HFMI to some degree, depending on this factor phi in principle. For the second question, which is regarding the maximum permissible stress, also the same data or measured traffic data were used, and they were correlated to the limits that I showed before, and it was found that safe estimation of the load effects to avoid having overloads that would result in relaxation of these residual stress could be achieved by checking the maximum load from the characteristic load combination. So that is also specified, let's say, in this case for that aspect. A couple of slides on the use of HFMI treatment for extending the fatigue life of existing bridges. This is typically could be the case when we meet situation in which we do fatigue assessments of existing bridges. The calculations show that the fatigue life is totally consumed, but inspection reveals no fatigue cracks. Or when we have bridges that have been in service and a change of conditions or situations, for example, allowing heavier traffic or increasing the traffic intensity, result in shortening the design fatigue life, and there is a need to extend the fatigue life. The principle or the hypothesis, let's say, for this method comes from the idea that fatigue damage is very localized at the well toe, as I mentioned before. And during the service life of the welded detail or of the bridge, fatigue will accumulate, assuming now that we don't have any cracks initiating at this region. If we at any period come and do the HFMI treatment on this detail, we will be able presumably to erase the fatigue damage that has been accumulated, and we would be this way able to extend the fatigue life or give the bridge a new fatigue life in principle. And this is something that has been investigated both our research group here at Chalmers, but also by other colleagues in various locations. I will show the principle of some of the tests that we've done here. So just to give a short background, where we've been testing different numbers of details in different conditions, both in as-welded, HFMI treated without any pre-fatiguing, and then pre-fatiguing the details and then doing some HFMI treatment or TIG dressing or a combination of TIG and HFMI, with the objective to see what can we achieve by this in terms of extending the fatigue life of existing details. So even though, as a disclaimer here, I would say it is not the intention that HFMI would be applied on a detail in which we detect during inspection of a bridge that cracks already exist. In the research work itself, in order to make sure that we are testing the worst condition or the worst scenario, what we've been doing is testing these different specimens until cracks of 1.52 millimeters deep are detected. Then we stop the fatigue testing, do the treatment, either directly HFMI or TIG remelting or a combination of these two. And then we continue fatigue loading and see what kind of extension do we get in fatigue life. That's in principle the method of verification. And the results can be shown in different ways. What we see here is the conventional SN curve, and we see new HFMI treated details without any pre-fatigue. These are the crosses that we see here. And then we see the triangles and the green circles, which are pre-fatigue details that after crack initiation were treated with HFMI. And it is obvious that, well, in all these cases, all the cracks were less than 1.5 millimeter deep, rather long in length, but through the thickness less than 1.5 millimeter. And what is obvious is that even in such situation, the HFMI treatment resulted in an extension of the fatigue life, similar to that would be obtained for a new welded detail, HFMI treated, which is extremely good, of course. So all test results fall above the SN curve 140, which is for this detail in a new condition. Another way of showing the detail is to plot the gain factor from HFMI treatment as a function of crack depth at the time of HFMI treatment. And this curve shows that if we have cracks less than 1.5 millimeters, we would be able to get a gain factor of 1, which corresponds then to, again, a new HFMI treated detail fatigue life. Similar things can be also said about TIG dressing. When TIG was applied on a cracked detail, under the condition that TIG dressing is deep enough to cover the full crack, then it produced results very similar to a new TIG dressed or treated details, which is, of course, very good also as well. Also, in the case of TIG dressing, in which the pre-existing crack is deeper than the area which were remelted, there was an enhancement in fatigue strength. Even with a remaining crack of 2 millimeters, we could observe an enhancement or an extension of the fatigue life corresponding to that of a new TIG as well. So that gives some degree of redundancy, let's say. So in principle, the idea then of using these methods in terms of fatigue life extension is that you have an existing bridge, you do a structural analysis, you identify the critical details, you go and inspect with some kind of NDT. If no cracks are detected, then HFMI treatment can be used, and one can assume a new HFMI life or fatigue resistance. If shallow cracks are detected, and these cracks are shallow enough to be covered by TIG dressing or to be remelted by TIG dressing, then TIG dressing followed by HFMI can be used to get a new HFMI life. Otherwise, of course, another method of treatment or repair or strengthening needs to be used. I see that I don't have much time to but I'll say maybe a couple of words regarding technical requirements. These are not in the Eurocode, of course. Requirements for the welds before HFMI treatment. In principle, the weld should fulfill quality level B. The fusion line or the weld to line should be clear and visible so that the treatment is placed on the right position. If the weld doesn't fulfill quality B and light grinding need to be used, for example, to meet quality B requirement, it can be done, but it should be done in a way that it doesn't erase the weld toe line, so that the operator who will do HFMI treatment can still trace the weld toe line. Sandblasting, of course, can be used both before and after HFMI treatment. However, all forms of thermal treatment are not allowed, both before and, of course, after HFMI treatment, because they affect both the microstructure of steel, but also the residual stresses and their distribution, and they result in relaxation of residual stresses. After HFMI weld treatment, again, all forms of thermal treatment is not permitted. Hot dip galvanization is, of course, not permitted. If HFMI treatment is done in the workshop for new bridges, it should be ensured, of course, that no operation done results in a relaxation of residual stresses. For example, if the bridge is to be launched, there is a risk of very high localized stresses that would result in a relaxation of the residual stresses, or maybe during erection, operation, transportation, and so on. So that needs to be taken care of. Sometimes HFMI treatment result in sharp grooves, like shown in the photo here. These might be threatening, but from the point of view of corrosion protection. Now you see the circle or the curve that you see, the depth of the groove here is around 0.2 millimeters. So these are very, very small. Still, they should be removed by light grinding and in order to ensure that we get a good coverage of the corrosion protection afterwards. In many cases, sandblasting would be enough to remove them. I'll skip this one and show this one instead, which is about the quality, qualitative or quantitative measures. Most important is the depth of the groove. This is different depending on the intensity setting of the tool, which is related actually to the steel. So for higher strength steel, this depth D would be a little bit more shallower than S355 or S275, typically in the range of 0.25 to 0.5 millimeters. It is also important to make sure that treatment covers both the base metal and the weld metal. So this length W should be something between 2 and 5 millimeters, and at least 25% of this is positioned then on either side, either the weld side or the base metal side. As to the radius of the groove, it depends on the pin used. Typically 3 or 5 millimeters pins are used for weld toe in general. There are different ways of measuring the quality. What you see here is a very simple way of using these gauges, but in some cases, laser scanners have been used to document that, but the measurement of the quality should be performed in order to make sure that these limits, let's say, particularly the depth of the indentation is correct. Visual inspection is important. It should cover 100% of the area which is treated. The surface of the HFMI groove should be smooth and shiny and without clear, distinct marks from the individual indenter strikes. It should be clear that no remaining traces of the weld fusion line is there. If there are undercuts that are in the size of 0.2 or 0.3 millimeters in the weld, then HFMI treatment will not be able to remove them totally, and then there will be traces remaining there. And in this case, this area needs to be ground, for example, and then treated again And in some cases, we've seen in practice that HFMI treatment, after the treatment, reveals or showed shallow local defects in terms of cold cracks or in terms of porosity that were revealed after the HFMI treatment. And this well needs to be treated, of course, gouged out, re-welded, and then retreated again. It cannot be allowed in this case. I have a couple of slides on documentation. I will not go through them, but they will be in the presentation with some proposals on what kind of documentations need to be provided by the client, the designer, and the operator, and the inspection people. That could be useful. A couple of fast slides about bridges in Sweden that the technique have been used. This is from the video I showed before. A lot of details, approximately 480 details, and these are the tropic decks were treated. Another railway bridge where critical welds between vertical stiffeners or diaphragms and bridge girders for a railway bridge short span were also treated. This is a new bridge. And this one is an existing bridge where built from 1963, which needed strengthening by welding longitudinal and vertical stiffeners on flanges and webs in different locations. And the ends of these stiffeners were critical with respect to fatigue. So HFMI treated will be applied now in the summer, the coming 2 weeks on these details in order to enhance the fatigue strength and fatigue performance. More work is ongoing because the rules now in the Eurocodes cover only carbon steel S235 to S700. But currently a lot of work is done both on stainless steel duplex and on weathering steel, and also new welded details, particularly cover plates, are underway also in terms of testing. So these rules could be extended more. I'll skip this documentation slides and conclude with the last slide where I left some references. If any of the audience is interested to get a deeper view of this, then you can have it there. And of course, you are always more than welcome to contact me if you have any questions other than what you will ask today, or if you need more material or any of these topics. So sorry for exceeding 4 minutes over my 40 minutes time, but that's what I had.
Thank you, Mohammed, for your interesting talk. For everyone, if you have any questions, please ask them in the chat right now. I saw a few already coming in. So if Mohammed, you want to respond to them, that would be very nice. The first question came from Johan Maljaars. Please, Johan, if you have anything to add after the answering on the question, just turn on your microphone and continue the discussion. He says, hello, Mohammed. Many thanks for your interesting talk. One of the barriers against applying HFMI in the bridges in the Netherlands is the absence of a quality standard, as we do have in welding. We are afraid that a lower fatigue strength than assumed after treatment because of under or over treatment. How do you cope with this in Sweden?
Yeah, that's a very good question. Of course, for the time being, there are no quality assurance or quality levels or measures connected to HFMI, for example, in 5817 or in 1090. And the way we've been doing it in Sweden is twofold. One is that we have our national recommendation on the quality measures and quality assurance with some recommendations on that. And the second one is that we followed what is also stipulated in the Eurocode, the upcoming version, by using the 3 qualified technologies. So the technology is one of the 3 that have been qualified, and they are qualified because the database that is used for the rules in Eurocode are based on these 3 providers and on their expertise, let's say, on doing the HFMI treatment. So these are the 2 ways of handling this question. Our own national description of the quality assurance and requirements, and making sure that the contractors who do the HFMI treatments belong to these qualified technologies.
Okay, thank you. He has an additional question as well, where he says post-well treatments particularly enhance the initiation life. For fully utilized details designed with D close to 1, this means that the propagation life in terms of time is shorter than for as welded details. This may imply that crack detection is less reliable, so we should perhaps only use the safe life approach for HFMI treated joints, for example, over like not relying on inspections as opposed to damage tolerant design. Perhaps we should do the same for non-welded details with mild notches. What is the practice in this respect in Sweden?
Oh, that's a very good question that I myself had not actually reflected upon. But indeed, absolutely. I wouldn't say there is any practice on, I mean, in Sweden, we don't use damage tolerant approach. We always use safe life approach. This has been the case lately, the last 2 years. Damage tolerant approach is allowed in very limited situations, but there is still a lot of discussion and argument whether this should be the case and what are the requirements on these details.
Okay.
So I have, at least in my thinking, been always assuming that safe life approach is used in design.
Okay, clear.
But I'm very grateful for the question. I need to reflect upon it more.
Then it's good to have this one-on-one talk maybe in a few days. Another question came from Noel Gresnicht. He is interesting to know how you measured the residual stresses after treatment at depth varying from 0 to 3 millimeters.
Well, this is done on test specimens in the lab, and we use X-ray diffraction. Actually, we have used 2 methods. X-ray diffraction, which would allow us to go maybe to 1 millimeter, 1.5. And in other situations, we use the hole drilling method also. So then we mount strain gauges and we drill holes at different levels and we measure the relaxation of strain.
Okay. And how HFMI can be done with UP, UIT, and HFIT, and possibly more tools. Is there any difference between them when applying them according to the Eurocode 199319?
Not really. I mean, there have been a lot of studies comparing different providers of technologies, and they show, in some cases, some variation, but very limited. But what we have in the derivation of the SN curves for the Eurocode is to use a database that contains all the tests produced by these 3 providers, or by tools by these 3 providers. So by doing so, we cover these 3 providers' tools in a good way. Of course, the operators are totally different, but the tools are these 3.
Okay. This is a question from Patrick de Cartier-Dive. I hope I pronounced it correctly. Are there criteria to reject or trash used pins? Roundness should probably be measured before using, I guess.
Pins?
Yeah, the pins that you do the treatment with.
Yeah, I mean, the pins are consumables, so they are used for I don't remember now the exact details. They are used for a specific length of treatment and replaced. And that is something that the operator has control over.
So, and then after they will be not reused anymore, but you have to use a new one.
Honestly, I don't know if they are treated somehow so that they can be reused, or if they are recycled, or.
Okay.
Yeah.
And then a question of Mohammad Lak. In case of a flat ground butt weld, HFMI will generate a notch and geometrical stress concentration details. Can HFMI be efficient in this case?
Yes, it is, because to some degree it is, because it produces these compressive residual stresses. But fatigue initiation usually in these kinds of wells, in many cases, starts from inner well defects, from porosity, for example, and these will not be affected by the HFMI. So the increase in fatigue strength for the butt wells, transversal butt wells, is less, let's say, compared to longitudinal attachment or transversal attachments, but it still has an effect. And this is apparent, of course, from the test results.
Okay. I think those were the questions so far. I do have an extra question. Would you consider that HFMI is once fully, of course, integrated in the Eurocode standards, etc., is a really proper way to treat wells, or would you still recommend using other techniques for specific situations?
I don't want to be partial in this answer, but my experience, I've been working with all three methods, both TIG and grinding and HFMI. And HFMI is much more efficient in terms of increase in fatigue strength, but it's also much faster and much more user-friendly.
Okay.
So I don't see, other than in situations where we are treating existing bridges with maybe shallow cracks, where TIG would be a very useful method, why any of the other two methods would be beneficial compared to HFMI.
Yeah, it's also beneficial because, of course, it increases the compressive strength and the hardness, etc. Yeah. How can people reach out if they have further questions or want to get in touch with you?
I mean, the easiest way is, of course, by email. I don't know if you can share my email in the presentation. I can put my email on the first slide.
We will add it as well in the presentation, I think. Yeah, we can do that.
Yeah.
Great. Well, Mohammad, then thank you very much for your interesting lecture today. For everyone else, we will put slides and the presentation on the website of Platform Stalen Bruggen en Bouwen met Staal, which will be shared later on. And Mohammad, thanks a lot. The flowers will be on your way from the Netherlands, so it might take a few days, but they are on their way. Well, for everyone else, thanks a lot for watching. Hope to see you soon. In October, we have a themamiddag, we call, on onderzoeken met impact. So please watch out for the newsletters from Platform Stalen Bruggen, where the date will be announced, the program will be announced, etc. Thank you very much.
Thank you.